we want to model the motion of a string. So it's a one-dimensional string that's plucked up and down, so we can make a wave on it. And I'm going to use finite difference method in Python, and that assumes breaking this into multiple pieces. And I've done this a couple times, but I always make mistakes. So I may make some mistakes here. This is not really the thing I'm super great at, but let's just get started. So here's my string. And so this string has a tension T, constant tension, and it has a linear mass density constant. Well, this is the mass density. So this is the mass per unit length. So I can break this into elements, even though it's not really that way. So I can imagine a bunch of finite masses connected by infinitely massless or massless strings. And I need to make a couple assumptions. One, that the tension's constant, that's actually, and two, that the motion of each element is only up and down. Okay. So with that, I want to write down Newton's second law for this one piece. So let's say these are all separated, these masses are all separated by a distance delta x. And this only works for small displacements. You know, if I have this too sharp, then my approximations don't work. So this is delta x right there. That would make that each mass is going to be equal to mu times delta x, right? Because this piece of the total linear density is mu divided by the length, then this piece occupies a delta x length. Okay, so that's the mass. I want to write down Newton's second law for this one mass right here, the ith mass. So I have the ith mass, I plus 1, I minus 1. So I can say the y force, F net y, is going to be equal to the mass, which is mu delta x, times the acceleration of that mass, which I will call the second derivative with respect to time of yi with respect to t. Yeah, that's the acceleration of that mass right there. And that's the actual derivative. We'll turn that into a finite derivative in a little bit. But what caused that to accelerate? Well, let's ignore the gravitational force. So I have two forces. I have a tension. Let's see. I'll call this T pulling that way, and I have a T pulling that way towards the other mass. So I have two T's. So the sum of those tension forces in the vertical components in the y direction are what matter. So let me just draw these two masses right here. So here's the mass I. Here's the mass I plus 1. This is I plus 1. And I have the tension is along that line. So if that's the case, this is delta x. This is delta y. So the tension is going to be equal. I can write Ty as T, the constant tension, times delta y over delta x. It's the ratio of that. That's a slope, right? And that will give me the y component. Now this only works for small angles. And so this angle right here has to be small. So if I look at that in terms of the ith and I plus 1 element, that t is going to be equal to, that's the y component, t times yi plus 1 minus yi, that's the change in y, and then the change in x is just delta x. Now what about the tension on the other side? Over here I have another mass, but it's pointing this way. So I can say the tension over here is going to be equal to the slope, but I want to go from here to there. So I'm going to go final minus initial. So this is my final. So I'm going to say t times yi minus 1 minus yi, all of that over delta t, delta x. So if I put that in up here, I get mu delta x, second derivative of y with respect to t, that's technically an I, is equal to the total, which is just going to be t times, I'll put these together, yi minus 1 minus yi, and then I have plus yi plus 1 minus yi, all of that over delta x. Okay, so now let me just divide both sides by this, and I get the following. I get the second derivative of yi with respect to time is t over mu times yi plus 1 plus yi minus 1 minus 2yi, all of that over delta x squared. Okay, so that's what I have. So what I've done is to deal with the changes in x as a finite difference. But I still have a real derivative over here. So let's take this y, and let's just imagine y as a function of time. And again, I take time, I look at one point on there, and I take time, and this is going to be y. And then, so as time moves on, I can break this into finite time pieces, and then again, I'd have finite y pieces. So this is going to be a different index, right? Because now I'm not using I, so let's use k. So this is going to be tk, let's call this tk, and this will be tk plus 1, and this will be tk minus 1. So if I want to take the derivative with the, and this will be yk, right? They're all terms in terms of k. I'm not doing index in terms of, I'm doing time indices. So if I want to find the slope right here of this curve, that'd be the first derivative. So one way to do that is to use these 2 points, right? So I can use y, I'll call it yk plus 1, yk minus 1. So if I find the slope between these two, I could say the derivative of y, not the first derivative of y with respect to time, is equal to the change in this. So it's going to be yk plus 1 minus yk minus 1 over the horizontal distance, which is time, which is 2 delta t. So these are delta t, divided by 2 delta t. So that's one way to do the first derivative. Okay, so that would give me the derivative at this midpoint. What I have the second derivative, though, how to do the second derivative? This is just the derivative of the derivatives, right? So I could say this is the slope at this point minus the slope at that point divided by the change in time between them, which is going to be delta t in this case. So the slope at this point, I can use these 2 points to find that slope. So this is going to be the slope at that point, which is a half, is going to be the change in y, which is yk plus 1 minus yk, all of that over delta t. That's that slope right there. And then I'm going to subtract off this slope, which is going to be the final, which is yk minus yk minus 1, all of that over delta t. And then I have to divide the whole thing by the distance from here to there, which is delta t. So I get the second derivative of y with respect to time is going to be equal to, I have a common denominator of delta t squared. I have yk plus 1 minus yk, and then I have minus yk, and then have minus a negative, so plus yk minus 1, and all of that over delta t squared. And so this gives me yk plus 1 plus yk minus 1 plus 2yk over delta t. So I actually have 2 indices for y, and I have for y. I have an I and a k. But that would be my second derivative with respect to time. So if I put that together with the other part, I get this. So I'm going to write the second, I have the second derivative of time is going to be equal to, I just wrote it down. Yeah, y, so I have 2 indices. So I'm going to say y, I, k, yeah, that's this second derivative over here. It's going to be this. K plus 1 plus y, I, k minus 1 minus 2yik, all of that over delta t squared. That's my second derivative. And then I can put that equal to the stuff on the other side, which was this, t over mu, which is just a constant, times, now over these are all, have a time indice of k, right? So I had to put that in there. So I'm going to say yi plus 1 k plus yi minus 1 k, that's all in indices, minus 2 yi k, all of that over delta x squared. So you see what I have. I have, in space, I have finite space out values and I have finite time values. What I want to do now is to solve for this. What do I want to solve for? I think I want to solve for, I just did this. I didn't want to make a mistake, so I wrote down a note. Just check my notes. I think I want to solve for y. I want to solve for this. I want to solve for the future position. That's what I want to do. Yeah. So solve for the future position. I want to solve for this value right here. So the first thing I'm going to do is multiply by t squared both sides. And I get, and then move that to the other side. I can do it one step. yi k plus 1, which is the future, right? That's the future value, is going to be equal to, I'm going to factor this out, t over mu, and then I get delta t squared over delta x squared. All that times this stuff. So I have yi plus 1k plus yi minus 1k minus 2yik. And then I have to subtract this stuff. So I get minus or plus 2ik minus yik minus 1. So let's just think about a picture. So this is y versus x, and I have elements. I do have boundary conditions, right? So I need to have these two. Oh, you can't even see that. These two set. So this is a distance L away. I need to. If it's a string, it's fixed at 2 points. So then I have this. So this is 0, 1, 2, 3, 4, 5. These are my I elements, right? So I have just 6. That's fine. And then I can have, I'll put it in another color. That's what I'll do. Do I have another marker? I had a green. Where do my colors go? Here's a purple. Okay. So then maybe a little bit later, I have this. And so these are, this would be the next time, right? So I have changes in time and I have changes in position. So the changes in time are the k's. So this would be actually 1, 1, right? So it's the time number 1, position number 1. This is time 0, position 0. Okay. So this says that if I want to find the next in time, which is going to be this position at the next time. That's what that says. I have some constant here. This is yi plus 1k. So this is the current time. K is k, but it's the next position, so it's that one. This is the previous position at that same time. This is the current position at the same time. This is the same thing, right? But it doesn't have that constant there, right? I could factor that out. That's a 2y. And then this is the previous time. So if I want to go through in space and I have these fixed, that's fine, right? Because I'm not going to change these. I can always look at the space before and the final space and just move through the middle parts. But in order to get the next time, I need the previous time. So I can't just start at t equals 0. I have to know t equals 0 and the previous time too. Okay. Okay, so we're kind of ready to do this. So here's what we're going to do. These space positions are going to be an array. A list in Python. In GlowScript Python, it'll be actually a list. So I have a list of values for all their y positions. And then I can change them to find the next time based on, I can't change that or that, but this position is going to depend on these two. This one's going to depend on these two, and so forth. And then the time will depend on the previous time and the current time. So I have to have 3 lists. I'll call this F new is the one I'm going to calculate right there in time. I have F now is the one that it's at right now, and that's a list. And then I have F old as the previous list. And so I'll go through, because see, if I want to find the new one, I need now and old. Now, to start this whole thing off, I'm going to give it some initial conditions, and I'm going to set both now and old to the same thing. And this would be what would happen if I like released it from rest, right? Because those are the same. There is a way to find the old for the first time, but let's just say these two are the same to start off. Start, same. Okay. Okay, let's jump into Python and do this. This is our main equation that we need right here. Let me double check that I have that same equation. I called this constant r squared. And we can just set that equal to 1, I think. Yeah, I think that's good. Okay, jumping to Python. I'm going to give you the code. Don't worry about that. Here we are. I'm using GlowScript v Python. Now, there are ways to do this, right? There are ways to do this that use special packages and stuff like that. But I like to do it from scratch. I like to just make it the way it is without having to do a lot of stuff that no one understands. So let's just get started. I want to go ahead and make a couple of things to begin with. I'm going to obviously graph this. So let's make a graph. G1 equals graph. Is that big enough for you? Graph. And I can give it an X title of X. I'm gonna plot the shape of the wire and then animate it with time. So because it's going to change in both space and time, so I need to do something. And then the Y title is equal to Y. And let's give it a width of 400 and a height of 200. Now, I am going to have to change something there later, but that's fine. And now it's something to plot. F1 equals G-curve. Color equals color.blue. Okay, now I need to pick my step size, my dx, and my dt. So let's just put those both at dx equals 0.05, dt equals 0.05. We can change that later. Now I need the length of the wire. Let's say length is 1 meter, and I need that r value of 1. I just picked a value. That's that constant, what is it, t over mu. T over mu is no. T over mu, r is actually equal to 1 times dt over dx. That's true. Yeah, because if I change that, I need to change that too. Pretty sure. Yeah. So so 1 is the t over mu. Okay. So now the first thing I'm going to do is make my list of x values. I do need x values. So I'm going to say x equals 0, an empty list. And let's say for temporary x, xt, in range. So the range function, I can give it a start value. I can give it a final value and a step size. So I'm going to say start at 0. The final value is going to be L. And then the step size is going to be dx. Now, but that won't work. Actually, that will give start at 0 and go up to L, but not include L. So in fact, I'm going to say plus dx. And let's change this dx to 0.2 just so we can see that it's working. And then I'm going to say print xt. That's we can check, right? It's always good to check that these things work. So that goes from 0 to 1. That's exactly what I wanted. So instead of printing that, I'm going to add that x equals x plus xt. So it's going to add to the list. And then after that, I can print my list of x's just so you can see that it works. Okay, so that is what we wanted. Now we can change this back to 0.05, and we don't need to print it. And I should probably at some point save this. So let's call this wave on a string finite difference. Okay. So now I have my x values. I need to create 3 lists: f old, f now, and f new. So let's just make lists for them. F old equals an empty list. F now equals an empty list. F new equals an empty list. And I will say for I in range length of x, right? So I want to go through, I want to have this the same as number of values for x. If I had a different number of f olds than I had x's, then it just gets weird. Now I could just go in and let's just do this, put these all as 0, because that's just the easiest thing to do. So f old equals f old plus 0. F now equals f now plus 0. F new equals f new plus 0. Actually, I don't think I want to do that, but I just did. Let's actually put our initial string as a sign function, because the sign function, I know I can fix that endpoint and the other endpoint at 0, and I can plot out those points. And let's just make these all the same. So let's just say up here, I'm going to say a equals 0.1. That's the amplitude of this. And then this is going to be equal to a times sine of pi times the x value, which is xi. And then so it's 2 pi, but if I want a half a wavelength on there, the wavelength would be a half. I think just sine pi. I think that works. So we can plot it. Okay, so there's my old. I'm gonna put the same thing for the now. Oops. The now and the new. So it should populate that. And now let's go ahead and print that. So for I in range, I could have done the same thing. Length of x, f1 dot plot. The x coordinate is going to be xi. The y coordinate is going to be, let's do f now I. And let's see if that works. You know, make some progress here. And see, good thing we checked because we have an error. Unexpected line, dx equals 0. Oh, okay. 0.5. Okay, so there's my wave. That's my starting wave. It starts at x equals 0. It ends at y equals 0. It ends at y equals 0. So that's a good starting thing to do. Okay, so I don't need to plot that, though. That was just a test. So I have my functions. Now I want to go through time, and for each time, calculate the new stuff. So let's just say t equals 0. I already have dt. And let's run this for 1 second. So while t is less than 1, I do need a rate statement. Let's do rate of 20. That'll do 20 calculations per second. It'll run fast, but that's fine, whatever. We can change that. So the first thing I need to do is, let's see, I need to, okay, one of the things I'm going to do is to make an animated graph, and I'll put a link down below to animated graphs, but the thing in an animated graph is to do this f data equals an empty list, and then I'll add data to this list and I'll plot that list. So instead of going through each point and plotting, I'm going to calculate that list and plot it. But I need to clear it at the beginning of each loop. So now I want to go in and calculate the new fi at that time from that previous time. So the new, let's see, so I'm going to say for I in range 1 length of x minus 1. So this will go from 1 to the length of x. Okay. It doesn't start at 0. And actually goes to x minus 1. So it doesn't go the whole way because I don't want to mess with the first data point or the last data point. I can't, right? Because I'm going to be using those in my list. So this doesn't go through the whole list. So now I can do what I said. F new of I equals, now I can type in my equation, which I had was r squared, right? Is it r squared? Yeah, r squared times y I plus 1, k. So since it has a k value, that means now. So I'm going to say f now I plus 1. And so now is k, right? Old is k minus 1. And then I plus 1 is the space. And then I have plus f now I minus 1. And so the now is k. And then I have minus 2 times y, or f now k, I. And that's, again, k. And this is all has to be parentheses up here. And then I'm going to say plus 2 times ik. So that's going to be 2f now I. And then I'm going to say minus, is that 2? Okay, I guess so. Minus, I think that's wrong. Let me check it. Minus 2 times I, so it's going to be, but k minus 1 means old. So f old I. Okay, let me just check. I think I got that wrong. I think I typed something wrong. Minus 2 f now f old. No, I think that's right. Okay. So that went through and calculated all the i's for the new time. That makes sense? Okay, what I need to do now is to change the olds into the nows, right? So I need to move all my lists up in time. So let's say for I in range length of x, because they're all the same length. I could do x minus 1, but I don't need to. Let's do this. Same thing. Let's not mess with the first and the last just to make sure they don't accidentally change. So what I'm going to go through is say the old elements is the now. So f old I equals f now I. And you can't just say f old equals f now, because that sets those two things pointing to the same data. You have to go through each element and change it. Now I want to change for I in range 1 length x minus 1. I want to change the nows into the news, right? Yeah, because I'm moving everything forward. So f now I equals f new I. Okay, so that's good. Now I want to go through and update my f data so I can plot it. So f data equals f data plus an xy coordinate. So my xy coordinate, my x is going to be x. So it's going to be, oh, I got to put this in a list. I could put this in a new, I'm doing a new loop, and that's probably not the best thing. But, you know, life is full of decisions that aren't the best thing. So for I in range, let's do the same thing. 1, I can just do the whole thing. Length of x. It should be fine. This needs to be indented. And then my x coordinate is going to be xi. So I'm going to put another list, xi. And then my y coordinate is going to be f new I. Now I can plot that data value. So I can say f1.data equals f data. That's the plotting part right there. Now I need to increase time. T equals t plus dt. If this works, you know, I don't know. Sometimes I think I feel like it's too complicated to work, but let's just run it and find out what happens. Saving it, running it. Say it didn't work. Unexpected range for I in length of x. Which, line 36. For I in range length of x. Oh. What the heck? I never did anything with that. Oh, no, I did. F xi f new I. It didn't like that. F data equals f data plus xi. unexpected token range for I in range in the length of X. Xi F new I. Let's just do this. Print I. Let's get rid of this. That's going to do a whole bunch of times. So let's do t is until t is 0.1. Let's just see if it runs. Unexpected. Okay, that's weird. Let's try this. Let's try changing this to ClosesScript 3.0 and then not printing f data xi f new I. It seems like they don't have the same length. Let's do this up here. Print length x print length f new. They should be the same. And didn't even print it. 37. It didn't print even that. Let's put print test. Let's see if it even gets here. No, it didn't even get there. Okay, let's do this. This is called troubleshooting. It's fun. So there's something wrong. In the worst case, I did actually type this out and it did work. Actually, I'm going to do that. Let's switch over. I don't know what my error is, but I did fix this. So I did cheat. Because, you know, you got to be prepared, right? This one works. So let's just change this. I said, let me get rid of this. Get rid of this. And then dedent, dedent. This should work. Okay, that's actually 2, but that's fine. So I start, see that's working. I mean, it's kind of amazing that it even works, right? I'm just kind of amazed that it works. And I don't know what that is different. This code looks the same. I'm going to copy this code and paste another one. I'm going to give you the code. I'm not sure where the mistake is. I don't want to waste an hour finding the mistake. But let's try this. One, that's a standing wave. That's what we'd expect, right? If you have the endpoints fixed, you get a standing wave. And so we won already. But let's make a non-standing wave. So over here, I'm going to put back what I had. Let's say if, what did I say? Xi is less than or equal to L over 2, then put the sine wave. Else, then I put zeros. Then else f old I equals 0. And in this case, what I did, I actually went through and made all zeros first, and then I did this. So that may be the problem. And then f now equals I. And I don't need to worry about f now I. I don't need to worry about the new because I'm going to calculate that anyway. So this will be half of a wave and then flat. Yeah, like that. And you can see a little jaggedness in there because it is finite elements right there. It's not continuous, but it's pretty good. You can definitely play with different initial wave functions, initial strings, change the time step, change the position step, and there you go. So, and I printed finish because something weird was happening there. Okay, so that's it. Wave on a string. There's a whole bunch of fun things to play with here. But I'll stop there. And I'm going to give you this code. If you have questions about graphing or something like that, I'll probably forget to put it in there. So just ask me and I will reply. But hopefully you had fun. I had fun because really I'm making this for me because I forget how to do this stuff. So that's that. Okay, talk to you later.